Chemical reactions do not occur instantly. Some reactions are very fast, while others are quite slow. For example, the neutralization reaction, where hydrochloric acid and sodium hydroxide neutralize, is extremely fast. On the other hand, rusting of iron is a rather slow reaction. Reaction rates may depend on several factors. First, the concentration of reactants. Generally speaking, the higher the concentration, the greater the speed of the reaction. A catalyst is a substance that by definition increases the rate of a reaction without being consumed in the process. Temperature. Most reactions proceed more quickly at higher temperature. And physical state. Most reactions proceed more quickly in the gas phase or in the liquid phase than in the solid phase. And if we are conducting a reaction in the solid phase, the reaction will go quickly if the material is very finely divided, and less quickly if it is in chunks. So now what exactly is meant by the reaction rate? Well, reaction rate is usually defined as the increase in the concentration of the product per unit time. Alternatively, we could use the decrease in the concentration of the reactant. Now, typically we use the molar concentration, so the unit would be moles per liter per second or moles per liter per minute for the rate. Recall that the shorthand for molar concentration is the substance, the chemical formula in the square brackets. Okay, so for example, we have the decomposition reaction. N2O5 decomposes to give NO2 and O2. This is a gas phase reaction, as you can see. We can specify the reaction rate by measuring the increase in the molar concentration of oxygen over time. So rate is delta O2 divided by delta T. Okay, so what is meant by this notation? The delta O2 represents a change in the concentration of oxygen. So we measure the concentration of oxygen at 2 times T1 and T2, and we subtract the concentration at the earlier time T1 from the concentration at the later time T2, and that gives us the change in the concentration of the oxygen. And then delta T is simply the difference in the 2 times. Now, if the time interval is very short, then this ratio here gives us a good measure of the instantaneous rate. In general, though, this ratio gives us the average rate of the reaction. So typically, for a reaction, we would get a graph something like this. Okay, so what we see is as time goes by, the molar concentration of the product increases, but the rate at which the reaction proceeds decreases over time. That is, as the reaction proceeds, it slows down. Okay, so consider these 2 points. For example, we measure after 20 minutes, and we find concentration of oxygen is 0.0035 molar. And we measure at 10 minutes, and we find that the concentration of oxygen is 0.002 molar. So then the change is 0.0015 molar. We divide by the time interval, 10 minutes, and we get the reaction rate. Okay, so 0.15 millimolar per liter per minute. That would be the average reaction rate in this time interval. If we make that calculation at a later time during the reaction, we find that the rate is slower. Okay? Only a third of the rate that we had earlier in the reaction. So same reaction, but now let's consider the rate of the decomposition of the N2O5. Okay, here's our original equation. We see this factor of 2 in front of the N2O5. So that means that it takes 2 moles of the N2O5 to generate 1 mole of the oxygen. And these stoichiometric coefficients can be used in general to relate the rates. Because this 2 is in front of the N2O5, it means in general that the N2O5 must decompose twice as fast as the rate at which oxygen is generated. Okay, here's another example. Oxalic acid, H2C2O4, is oxidized in acidic solution by permanganate to carbon dioxide and water. Here's the balanced equation. Okay, lots of stoichiometric coefficients. We need to relate the rate of decomposition of oxalic acid to the rate of formation of the CO2. So what do we need to do? Well, all we need to do is look at the coefficients. We see there's a coefficient of 10 in front of the carbon dioxide and a coefficient of 5 in front of the oxalic acid. So that means that the carbon dioxide is generated at twice the rate at which the oxalic acid is decomposed. Okay, and symbolically, we can write it like this. Now, what does this negative sign mean? Well, that just means that the oxalic acid is decomposing, whereas the carbon dioxide is being generated. Okay, second question. Relate the rate of decomposition of oxalic acid to the rate of formation of the manganese 2+ ion. So we look back at the balanced equation. We see that the manganese ion has the 2 in front of it, and the oxalic acid has the 5. So that means that the coefficient that relates those two substances is 5/2. The oxalic acid decomposes at 5/2 the rate at which the manganese ion is being generated.